Okay, last time we stopped here. Right? We're talking about the dispatch latency and the functionality of scheduler and dispatcher. CPU scheduling usually make decisions based on the following criteria: utilization, okay, and throughput, the number of job can be completed in a time unit, and turnaround time usually defined as to be the total latency for a particular process from start to terminate. Okay, waiting time usually defined to be the total amount of time that a process is waiting for other waiting, okay, instead of using CPU. Okay, so usually waiting time would be the turnaround time minus total CPU time. Okay, and the response time usually is defined for interactive jobs. Okay, for a batch task, it's not it's irrelevant. Okay, but for the interactive job, usually we try to measure the request and the response, the time between the request and the response. Okay, so usually it's defined to be the latency that a process take and a new request and produce the response for that particular request. Okay, so during the life cycle of particular process, it may loop between the CPU burst and the I/O, right? So when the I/O receive a new request, and then you go to the CPU burst to generate result, and then go to the I/O to generate output. Okay, so the latency between get a new request to the first response generated will be the response time. Okay, and time slice, or sometimes we call it time quantum, is the maximum time allowed for a particular thread to use CPU before being preempted. Okay, so every time when scheduler select a particular process, the dispatcher assign the CPU to that particular process, and the time for a particular process to use CPU. Okay, for each time, each cycle. Okay, or each assignment. Okay, and for this particular assignment, you can only use to a time quantum. Okay, when the process use up all the time assigned for this particular time quantum, then the process of thread must be preempted. Okay, and CPU can be reassigned to other process. Okay, and unless the running process or voluntarily issue a system call, so then the CPU access usage will be preempted. Okay, before the time quantum expire. Okay, now we will introduce some typical CPU scheduling algorithm. The first one is first come, first serve, okay, or FCFS scheduling. That means the process which arrived the system or created first, earliest will get scheduled early. Okay, first. Okay, so an example is something like this. If we have a 3 process P1, P2, P3, and their burst time means that the next CPU burst, the time required for the next CPU burst is 24 time unit and 3 unit. Okay, each. Okay, assume the process arrived in the order of P1 followed by P2 and P3. Okay, so the index stands for their arriving sequence or order. Then the Gantt chart for the scheduling will be like this. So assume that P1 is arrived system or created in time 0. Then it will be immediately assigned, because when the time in time 0, there's no process using CPU. Okay, and the P1 require 24 time unit. So in the time 24, P2 will be scheduled. Okay, and then in 27, P3 will be scheduled. So the waiting time for these 3 processes, P1 will be 0 because when P1 arrive and immediately scheduled. Okay, and P2 will be 24. Assume they all arrive in time 0, but in the order of P1, P2, P3. Okay, they all arrive in time 0. Okay, and P3 will be 27 because P3 started time 27. Okay, and average waiting time for this, it will be 0 plus 24 plus 27 divided by 3. It will be 17. Okay, so that's for the first come first serve. Okay, although their arriving time are all the same for time 0, but they still has slightly difference. The order will be okay. So if those process arrive in different order, okay, they all arrive in time 0, but with different order. P2 first, followed by P3 and P1. Then again chart. Then for first come first serve scheduling, P2 will be scheduled immediately, and then in time 3. Time unit 3, P3 will be scheduled, and then in time unit 6, P1 will be scheduled. So the waiting time for P1 will be 6, P2 will be 0, P3 will be 3, and the average waiting time will become 6 plus 0 plus 3 divided by 3 is 6. So you can see the average waiting time for this set of processes is much less than the previous one, this one. Okay, the setup process is the same, P1, P2, P3, and their burst time are the same. Only difference is the arriving order. They all arrive in time 0, but with slightly different orders. Okay, P1 followed by P2 and P3, and then here is P2 followed by P3 and P1. So, and the schedule difference, you can see that the job require more CPU time with scheduling data. Then the average waiting time will become less. So this is a very interesting phenomenon. We call it convoy effect. Okay, a short process may be slowed down by a long process. If we schedule a long process before a shorter process, then the short process will wait for a long time, and the average waiting time will be increased. Okay. However, if we schedule short process first, then relative to the long process, then the average waiting time can be reduced. Okay. So eventually we have this shortest job first scheduling. So if you have a set of process, they arrive in simultaneously, almost at the same time. Then schedule the shorter process first will lead to less average waiting time. Okay. If we associate each process with the length of its next CPU burst, then use the length to schedule the shortest process first. Okay, and in some sense, if the optimization criterion is the waiting time or average waiting time, then shortest job first will be treated and considered to be optimal with respect to average waiting time for a given set of processes. Okay, if those set of processes they are all arriving in the same time. And the difficulty for this, so it's optimal, okay, in some sense. Okay, but however, the requirement is that we know the next CPU burst. We know precisely the time for each process is the next CPU burst. Okay, and that's the difficult because in general we don't know the next CPU burst time of each process. Okay. And if the shortest job first, if those process, a set of process, they are not arrived in the same time, but arrive in has the time difference. Okay, then the shortest job first will have two versions. One is non-preemptive shortest job first. That means once a process was assigned to CPU, then it will use up all its CPU burst time, and then the CPU schedule a state another one. Okay, for example, consider this set of process P1, P2, P3, and P4, and they have different arriving time, okay, and burst time. So the non-preemptive shortest job first schedule will generate this scan chart. Okay, P1 will be scheduled immediately in time 0, and after 7 time units, okay, P2, P3 will be scheduled because in time unit 7, P2 and P3 and P4 they are all arrived. However, the shortest CPU burst time for these three processes, P3 has the shortest one. Okay, so P3 is scheduled first, and so in the time unit 8, P3 finish. Then we have P2 and P4. They have same CPU burst. So either way is all right. Okay, assume we use the smaller index first. So then we schedule P2 from time unit 8 to 12, and followed by P4 from time unit 12 to 16. Okay, and now the average waiting time will be 0 for P1 plus 6 for P2 because P2 started in time unit 8, but P2 arrived in time unit 2. So the waiting time is A minus 2 will be 6. And P3 started in time unit 7, but it arrived in time unit 4. So it will be 7 minus 4 will be 3. For the P4, it started from time unit 12, but it arrived in time unit 5. So it's 7 minus 12 minus 5, it will be 7. Okay, so 0 plus 6 plus 3 plus 7 divided by 4 is 4. So for non-preemptive short job first scheduling, okay, for this set of process, they have an average waiting time will be 4. Okay, if we allow preemption for this short job first, that means if a newly arrived process has higher priority, that means the remaining time of the current running process is longer than the newly arrived process, then we will preempt the current running process and let the newly arrived process running first. Okay, then this kind of scheduling is called preemptive short job first, or sometimes we call it shortest remaining time first. Okay, so shortest remaining time first also is preemptive shortest job first. For the same set of process P1, P2, P3, P4 with the same parameters, their arriving time and burst time. Now, if we using shortest remaining time first, then P1 will schedule in 0, but in time unit 2, because P2 comes in, arrive, and P2 require 4 time unit, and the remaining time for P1 is 5. So P2 will be scheduled, and P1 will be preempt. Okay, so P2 will start running in time unit 2. However, when in time unit 4, P3 arrived. Okay, and P3 has CPU burst time 1, and in that time P2 has remaining time 2, and P1 has remaining time 5. So these 3 ready process, P3 is shortest. So P3 will preempt P2. So P3 will start running in 4 time unit. And in time unit 5, P3 finish and P4 comes in. And P4 has 4 CPU burst time remaining. P2 has 2 and P3, P1 has 5. Okay, so P2 will be scheduled for and then again in time unit 5 and finish in time unit 7. And then P4 and P1, they are already, and P4 has remaining time 4 in time unit. P1 has remaining time 5 in time unit. So P4 will get first and it's from 7 to time unit 11. Then P1 followed by the remaining part starting from time unit 11 to time unit 16. Now the average waiting time for P1 will be what? You can see that P1 arrived in time 0 and finish in time 16. So total turnaround time for P1 will be 16, but its burst time is 7. So the waiting time for P1 will be 16 minus 7, so it's 9. For P2, the finish time for P2 is 4, and the burst time is 4. So that means there's no waiting for P2. So waiting time for P2 will be P2 finish in 7, and burst time is 4. So 7 minus 4, the turnaround time is 5. Okay, P2 starting from 2 and finish in 7. 7 minus 2 is 5. So turnaround time for P2 is 5, and the burst time is 4. So waiting time for P2 is 1. Okay, for P3, arriving time is 4. Finish time is 5. Okay, so turnaround time is 1, and burst time is 1. So there's no waiting time for P1. So it's 0. For P4, arriving time is 5. Finish time is 11. So turnaround time for P4 will be 11 minus 5, 6. And burst time is 4. So 6 minus 4, the waiting time will be 2. Okay. So total, the total waiting time is 9 plus 1 plus 0 plus 2 divided by 4. So the average waiting time will be 3. You can see that this preemptive shortest job first or shortest remaining time first has greater or smaller average waiting time than this non-preemptive shortest job first, which is 4. Okay. So if preemption is allowed, then we should use preemptive shortest job first. Okay. If we know the next CPU burst time of each process, okay, it's optimal. Okay. And how to estimate or get the next CPU burst time? Okay. In general, we can only estimate. You cannot get a real one. Okay. So a typical estimation is using weighted exponential averaging of previous CPU burst times, and this way may be adjusted to the recent CPU burst time as more weight than the others. Okay. For example, if we have used T sub n, is defined the actual length of the nth CPU burst time for a particular process, and tau sub n plus 1 is the predicted value for the next CPU burst time. Okay. And then alpha, be it a parameter, is between 0 to 1. And we can define the next CPU burst time, tau sub n plus 1, will be the alpha times T sub n plus 1 minus alpha times tau sub n. That means we use the previous burst time, actual burst time, T sub n, and its estimation, okay, tau sub n, okay, and with different parameter alpha and 1 minus alpha, okay, and this weighted average of this real CPU burst, the previous CPU the real actual CPU burst time, and the estimated CPU burst time of previous CPU burst. Okay. Then we can define this to estimate the next CPU burst time. To extend this tau n sub n plus 1, we can get the following two formulas. Okay, so eventually a tau sub n plus 1 will be something like this. It depends on previous actual CPU burst times. Okay. And this estimation is typically used, and if we don't know, alpha can be very close to 1. If alpha set to 1, that means you use the previous actual CPU burst time, the last CPU burst time, to estimate the next one. Okay, if we use half tau, use 0.5, then you treat the actual CPU burst time of last CPU burst and its previous estimation, okay, as equal weight. Okay, then typically we use these two parameters. Alpha is 0.5 or 1. Okay, these are very common. So if we can estimate next CPU burst time with high probability, okay, of accuracy, then this remaining time first or shortage jump first can achieve a very good average waiting time, okay, of processes. Okay. Now let's discuss next very commonly used scheduling policy you call round robin. Okay, round robin is used very often for time sharing systems. Okay, that means we try to assign CPU equally to all the process which is connected in the memory. Okay, in the ready queue. Okay, so for example, you have an n process is ready in ready queue. Then try to assign 1 over n CPU times to each process. Okay, so let every process anticipate this illusion that it get a slower CPU dedicated to itself. Okay, so that's a very good estimate illusion for that. Okay, so each thread get a small unit of CPU time. Okay, time quantum, and they are all get the same time quantum for each. Okay, for example, usually you set to 10 to 100 milliseconds, and after time slide expand, the thread is preempted and put back to the end of the ready queue. And the process in front of the ready queue in the first will be selected as the next candidate. Okay, if there are n thread in the ready queue, then the time quantum is q. Then each thread gets 1 over n CPU time in chunk of at the most q time unit at once. Okay, so no thread will weigh more than n minus 1 q time units. Okay, of course, some thread may prematurely be suspended because it issue a system call waiting for other IO devices. Then the CPU usage will be took off. Okay, taken back by the CPU and reassigned to other process. Okay, but the maximum waiting time, okay, will be less than n minus 1 times q time units. Okay, and the performance of this round robin scheduling, if q is very large, then similar to first come first serve. Okay, because q is large enough, so most of the time, so q is larger than next CPU burst of all the processes. Then it's a first come first serve. Okay, or first in first out. If q is small, but q must be larger enough with respect to the context switching time. Okay, otherwise the overhead for context switching become too huge. Okay, so in general, we require the overhead of context switch will be within 5% or 10% of the Q the time quantum. Okay, then it's smaller, but it's big enough to cope with the context region time. Okay, otherwise true. Okay, so if Q is small, then it look like a time period system. Okay, so every process get 1/n CPU time unit. Okay, yeah, fairly. Okay. The next is priority scheduling. Okay, shortest job first is some kind of priority that use the CPU burst time. Next CPU burst as the priority. Okay, shorter one get high priority. Okay, but in general, a priority number or integer is associated with each process, and this priority number can be anything humanly, artificially defined. Okay, it may be the user's ID or user's privilege. Okay, different class of users. Okay, such as the user may get the highest priority, and normal application programmer get the second, and then the student get the lowest priority. Okay, so something like that. Okay, it's all right. Okay, so a priority number is associated with each thread. The CPU is allocated to the thread or process with the highest priority. Okay, and this scheduling can be either preemptive or non-preemptive. It's just like shortest job first. Okay, so shortest job first is a priority scheduling. Priority is the predicted or estimated next CPU burst time. Okay. The problem for this priority scheduling, okay, it's good. The average waiting time, okay, if the next CPU burst time is the priority, then it can get the optimal average waiting time. Okay. However, it may lead to starvation. Okay, some low priority task may never get executed because always has a newly arrived process or thread is higher priority than the waiting one. Okay, to avoid starvation for some low priority process, a typical mechanism is called aging. Okay, so when a process waiting in the system longer, then its priority will be increased for according to its waiting time. Okay, this sometimes we call it aging. Okay, a time progress increase the priority of each thread when time. Okay, so the priority can be negative related to its waiting time. Okay, you set create an aging function. Okay, whenever so for example every 10 millisecond or every minute, okay, pass by the priority of a process will automatically increase by 1 or something like that. Then eventually the process is wait long enough will become the highest priority job. Sometimes it's difficult to schedule all the process according to one particular scheduling policies because the task or the thread or process their characteristic may be very different. Okay, so another interesting scheduling policy we call multi-level queues. That means different characteristic, the task with different characteristics, they are assigned to different waiting queues. Okay, and different waiting queue or waiting use different scheduling policy. Okay, so try to maximize or let every process be scheduled according to its characteristic. Okay, so this type of scheduling policy we call it multi-level queues. The ready queue is partitioned into several queues. For example, that is two kind of process. One is interactive jobs. Okay, so for this kind of job, it require the response for each request will be fast enough. Okay, so sometimes we call this kind of job, foreground jobs. Okay, so the user is interactively interact with the system. The second time we call background task or batch task. Okay, it means once we submit this kind of task, create this process, user you can just go ahead to do other things because it expect the process run for a long time and then generate result. And during this execution of the process, the user did not need to interact with the program. Okay, they're just in the beginning, and then they were waiting for the final outcome. Okay, so for these two kind of processes, their scheduling part should be different, right? Because the requirement is different. Okay, so each queue has its own scheduling algorithm. For foreground, usually we use round robin because they are interactive. They ask for a short response time. Okay, once you submit a request, you expect to get the response in a few minutes, a few seconds. Okay, in a short time. So they should be scheduled according to something like round robin. Okay, so every process get fair amount of CPU time. Okay. And for the background task, the first come first should be all right because once you submit, you expect a long time, a long turnaround time, and then you get a response. So usually, user only communicate or interact with the system in the beginning, in the creation time, and in the end. Okay, user don't interact with the task in the middle. Okay, so once you submit, then you go ahead to do something else. Eventually, you get notified, so the outcome is come. Then you pick up the outcome. Okay, so first come first, it's all right for this kind of task. Okay, and because you have two queues, so how to arrange these two queues, the process in different queues. Okay, you can either use fixed priority scheduling, so serve all the process from foreground queue, okay, and then background queues. But if this fixed priority scheduling is used, then the background task may never get scheduled because if there's always as new inter or new foreground job comes, then the background job may get stuck. Okay, so next possible alternative is time slicing. Okay, each queue get a certain amount of CPU time, and then during for that particular CPU time, is scheduled its own queues. Process in its own queues. For example, can 80% of CPU time allocated to foreground task in round robin fashion, and 20% of CPU time is assigned to the foreground job or to the background job, and they are running in first come first serve. Okay. So we may use a mini as the time quantum. So during each minute, the first 80% of a minute will be scheduled for the round robin queues, and the last 20% of minute will be scheduled to the first come first serve queues. Okay, of course, to doing this kind of time slicing mechanism, the scheduler almost it must be preemptive. Okay, so either round robin can be preemptive, and the first come first serve it need to be preemptive because when it's time or for scheduling process from round robin, then the background job need to be preemptive. Okay, and so on. So between the queues, they are preemptive, but within the queues, round robin is preemptive, and within the first come first serve is non-preemptive. Okay, but between the queues is preemptive. Okay. So here is an example. We have a highest priority for system process, interactive process, editing process, batch process, and student process. For example, we have just 5 different queues. And the priority is something like the highest priority is system processes. Okay, and every queue may have different scheduling. Can use different scheduling policy for that particular type of processes. Okay, and typical way is we assign the CPU usage according to their percentage. Okay, so maybe you have 40% of CPU running system process and 30% running interactive process, 20% running this interactive editing process, and 9% for batch process, 1% for student process, for example, something like this. Okay. For this multi-queue, multi-label queue scheduling, when the process create, during the creation, the system need to have some prior knowledge to decide to recognize the property of this process, and then assign the process to the proper queues. Okay, and once the process been assigned there, so it just loop in the particular ready queue. Okay, after for each CPU burst, after CPU burst, you go to the I/O, and then finish I/O, you go back to the original waiting queue also. Okay, so the process will not moving among these ready queues. Okay, however, again, it has a problem how to decide the property of this process when we create a new process. For student process, of course, it's easy because for those the process created by a student ID, then we know. But for system process or interactive process or whatever, okay, if it's a operator or the staff, okay, in university, the researchers and staff, they use ID, okay, they all have the same class of use ID. Then how do we distinguish it and separate, distinguish it is an interactive process, it is an interactive editing process or batch process. Okay, okay. To find out or classify this process into the proper queue. Okay? If we did not classify it right, then the overall system throughput or the response to that particular task may become not user friendly. The user may be not satisfied. Okay. So another policy scheduling mechanism we call it multi-level feedback queue was introduced. Okay. So it means it allows a process to move around these various queues. So initially we assign a process to a particular queue, and then to find out this the behavior of the process is not proper for that particular queue. Then you can move the process to other queues. Okay. And for example, agent can be implemented in something like this. Okay. So if we have a lowest priority task in the first come first serve queue, and then we assign using agent to mechanism. So the priority of a process may be changed, and eventually the process can move from the bottom queue to the upper higher level queues. Okay, so multi-level feedback queue scheduling will define some of was defined according to the following parameter: the number of queues and schedule algorithm for each queue. A method to use to determine when to upgrade a process from the bottom queue to the upper queue, and measures used to determine when to demo a process, okay, from upper queue and down down to a bottom queue. Okay, a measure user determine which queue a process will enter when the process needs services. Okay, so something like this. Okay. For example, a typical multi-level feedback queue may contain 3 queues. The Q0, the highest one, is round robin with time quantum set to 8 milliseconds. And the second queue, Q1, is also round robin with time, but with time quantum high, slightly longer time quantum, say for example 16 milliseconds. And the last queue, Q2, is first come first serve. Okay, so initially all the newly created process was enter in the Q0. Okay, put in. So we don't need to classify. Okay, and put it into the rear of the Q0. Okay, when a job in Q0 get the CPU access, it receives 8 milliseconds as its time quantum. Okay, if it does not finish in 8 milliseconds, the job is moved to the rear of the queue. That means within 8 milliseconds, the particular process call a system call. So it releases its CPU usage voluntarily. Then the process, after it finish IO complete, the process will stay in this Q0. Okay, because 8 milliseconds is good enough for that particular process. That means every interaction CPU burst is less than 8 milliseconds. Then it's remain in the Q0. Okay. If